So our next chapter in quantitative analysis deals with diprotic and dibasic systems. A diprotic acid has two protons that can be given up, and the general formula H2A we'll use for it. A dibasic base is capable of producing two hydroxides stoichiometrically. In other words, it is capable of accepting two protons under the Bronsted-Lowry theory. An example of a polyprotic system are amino acids. Amino acids have a general structure that's got a central carbon atom, a carboxyl group on one side, and an amino group on another side. This central carbon atom has some bond to some R group, and this R group is the distinguishing feature of the amino acid. So this changes as amino acids' identities change. When amino acids come into contact with water and mix, they can deprotonate. In a neutral solution, this deprotonation transfers a proton from the carboxylic end of the acid to the amino end of the acid, and we come up with a structure that looks like this. Very similar in structure at the center, but the carboxylic end of this amino acid is negatively charged, whereas the amino end of this acid is positively charged. So we come up with a structure that has two charges on it at two different locations. A structure with two charges on the same molecule at two different locations is called a zwitterion. So in a neutral solution, where we've mixed our amino acid in neutral pH water, we arrive at the zwitterionic form of our amino acid. We can give the general formula HL to this zwitterionic amino acid. Suppose instead that we place this amino acid in an acidic pH solution, so that in pH less than 7, it forms a structure that might look like this, remaining protonated at the carboxylic end due to an excess of hydrogen ions in solution, but also protonating at the amino end. This is a positively charged cation now. This cation will give the general formula H2L plus. Lastly, let's imagine placing our amino acid in a basic solution where pH is much greater than 7. We would expect deprotonation of our amino acid at the carboxylic end, but not a protonation event at our amino end. So our amino acid might end up looking like this. Deprotonated at the carboxylic end with an amino side intact as normal. We might call this L-. Therefore, we can expect to see two deprotonation events for our generic amino acid. In one deprotonation, our fully protonated H2L plus form gives up one of its protons to generate the HL, or zwitterionic form of our amino acid. That's this acid losing a proton to become this one. In a second deprotonation event, our zwitterionic form, HL, can lose a proton and form the deprotonated form of our amino acid, L-. That's this form over here. These two deprotonation events are associated with Ka1 for the loss of the first proton from the fully protonated form of our amino acid, and Ka2 from the loss of our second proton from the zwitterionic form. So let's look at a real example of amino acid leucine, Leucine has the structure that I've drawn here, and leucine hydrochloride is the fully protonated version of this amino acid. And the fully protonated version of the amino acid, this amino group is fully protonated, and we have 3 protons rather than 2. Positive side over there, we can give this the general formula, H2L plus, and call it leucine hydrochloride. Leucine hydrochloride has a Ka1 of 4.7 times 10 to the minus 3, and a Ka2 of 1.8 times 10 to the minus 10. We're going to come up with a pH of a 0.5 molar leucine hydrochloride solution. So, in order to accomplish this, we need to think about 2 observations from these data. For one thing, the pKa for the first deprotonation event suggests that H2L plus is a weak acid. Its Ka is less than 1. So H2L plus is weak. We can treat it similarly to the way that we've treated weak acids in the past. Secondly, even though H2L plus is weak, it's still stronger than HL, the zwitterionic form of this acid. So HL is much weaker. In fact, it's weaker by 7 orders of magnitude. That suggests that whatever HL, this zwitterionic form, is produced in the course of H2L deprotonating, itself hardly dissociates at all. Therefore, it might be helpful for us to think about H2L plus acting like a monoprotic weak acid. If it acts like a monoprotic weak acid, then the bulk of H plus that comes from H2L plus is really the only source of H plus of any appreciable amount in solution. We'll deal with our H2L plus as if it were a monoprotic weak acid, and we solve monoprotic weak acid problems with this approximation. Here, our Ka value is really the Ka1 from the deprotonation event of our fully protonated leucine hydrochloride. Our X is the approximate amount of H plus cation in solution produced primarily from leucine hydrochloride, and F is our formal concentration. So plug in the numbers that we have from our problem above, 4.7 times 10 to the minus 3. This is our Ka1. That's equal to X squared, our hydrogen ion concentration from leucine hydrochloride, over our formal concentration of the substance, 0.5 molar. Solving this equation for X, we get 1.53 times 10 to the minus 2 molar. All right, just like normal, we'll check to make sure that our assumption works out appropriately. Calculate alpha, that's X over F, 1.53 times 10 to the minus 2 divided by our molar concentration of leucine hydrochloride ends up as 31%. Oh no. So this result means that we have to solve the quadratic equation explicitly in figuring out the molar concentration of H plus cations. At equilibrium, we have to add in the extra factor of F minus X to our expression from above. In solving the quadratic equation, we come up with this formula. A term of C of 2.35 times 10 to the minus 4. We get 2 solutions for X. We'll reject one that doesn't make any physical sense and keep 1.32 times 10 to the minus 2 molar as our X solution appropriate for this problem. From this value, we calculate a pH of our leucine hydrochloride solution. That's equal to 1.88. So let's validate the assumption that there is an insignificant amount of H plus produced from the zwitterionic form of our amino acid HL. The deprotonation event for HL looks like the equation that I've drawn here, and it has a value of Ka2 of 1.80 times 10 to the minus 10. We know from our work above that the concentration of H plus produced from our fully protonated version, H2L plus, must be equal to the concentration of our zwitterionic form, HL, that is 1.32 times 10 to the minus 2 molar. Further, we know that Ka2 has an equilibrium constant expression given as concentration of H plus times concentration of L minus over concentration of HL. Given our assumption, if these two things, H plus and HL, are for all intents and purposes equal to each other, if H2L plus is the primary source of H plus cations in solution, then that would mean that HL's and H plus's concentrations can be eliminated in this expression, and we arrive at the result that the concentration of L minus is effectively 1.8 times 10 to the minus 10. This is an estimate of how much H plus is produced from the zwitterionic form of our amino acid, and notice that this is 8 orders of magnitude smaller than the value of H plus concentration produced from the fully protonated version of our amino acid. This validates our assumption and tells us that we can ignore the zwitterionic form for the purposes of calculating the pH of a fully protonated acid. When we deal with fully protonated weak acids, we can treat them as though they're monoprotic acids as a good first approximation. In keeping with our model study of the amino acid leucine, we're going to next study the fully deprotonated form of this amino acid, leucinate. The deprotonated form we can call L minus, and we're going to calculate the pH of a 0.5 molar solution of leucinate L minus. There are two reactions that leucinate can undergo. It can undergo two protonation events by abstracting a proton from water. In each one, it's acting like a base. The first protonation event we'll call KB1, and the second one, where the zwitterion accepts another proton from another water molecule, we'll refer to as KB2. We weren't given explicit information about either KB1 or KB2. So the first thing that we need to do, the first aside that we'll need to take, is thinking about how we determine the value for KB1 and for KB2. So here what I've done as an aside is mapped out a series of 4 reactions representative of some generic diprotic weak acid, H2A. In the first, H2A deprotonates to form a single proton and HA-. The equilibrium constant for this reaction is given as Ka1. In the second, HA- deprotonates one more time with equilibrium constant Ka2. Of these two reactions, Ka1 represents the more acidic acid. This is because it's easier to lose a first proton than it is to lose a second. Similarly, in reactions 3 and 4, we represent the base activity of the conjugates A2- and HA-. Of these, KB1 is the more basic because it's easier to accept your first proton than it is to accept your second. So what we'll do over the course of this intermission is talk about reactions 1 and 4 comparatively, and 2 and 3. In reactions 1 and 4, we have first H2A deprotonating to H plus plus HA-, equilibrium constant Ka1. In reaction 4, HA- reacts with water to form H2A and hydroxide. Equilibrium constant here is Kb2. Suppose that we add these two reactions together, what do we get? Well, things that are the same on both sides of our reaction go away. That's HA minuses, H2As. We end up with our autoionization of water. H2O, H plus, OH minus, Kw. This suggests that if we multiply the equilibrium constants Ka1 and Kb2, we should get Kw. Similarly, comparing reactions 2 and 3, HA minus deprotonates to form H plus A2 minus, given by Ka2, or A2 minus reacts with water to form HA minus plus OH minus, given by Kb1. Add these two reactions together, and again, we end up with the autoionization of water. This suggests to us that Ka2 times Kb1 gives us Kw. With that aside, we can solve for the Kb1 and Kb2 of our base leucinate up above. Kb1 must be equal to Kw over Ka2, 1 times 10 to the minus 14, over our Ka2 value, which was 1.8, times 10 to the minus 10, 5.56 times 10 to the minus 5. Similarly, Kb2 is Kw over Ka1. That's 1 times 10 to the minus 14. Over our Ka1 value, which was 4.7 times 10 to the minus 3, giving us 2.13 times 10 to the minus 12. And just like we expect, Kb1 is greater than Kb2. So, similarly to our previous attempt at solving the pH of a solution of fully protonated form of our amino acid, the fully deprotonated form has a significantly larger Kb1 than Kb2. This suggests that the production of hydroxide ion from reaction 1, Kb1, will dominate the pH in the solution. And so we can approximate the fully deprotonated form of leucine, leucinate, as a monobasic weak base. And we can start with the approximation that Kb1 is equal to x squared over F, where again x is indicative of our concentration of major species, in this case hydroxide ions, in solution. Solve for x, 5.56 times 10 to the minus 5 is equal to x squared over 0.5 in a 0.5 molar solution of leucinate. X is equal to 1.67 times 10 to the minus 3 molar by approximation. As always, we'll check this assumption to make sure that we can carry out the easy form of this calculation. Alpha is x over F, 1.67 times 10 to the minus 3 over our formal concentration, 0.5, giving us 3.3%. Phew, we're okay. So we can live with our assumption. We don't have to solve a quadratic equation. We can calculate first the pOH of this solution. Take the negative log of 1.67 times 10 to the minus 3. That's 2.78. Therefore, the pH of the solution, 14 minus 2.78, is 11.22. Again, if we use the approximation that hydroxide ion is from our first reaction approximately equal to the concentration of Zwitter ion, HL, in our solution. And this is 1.67 times 10 to the minus 3. It suggests that H2L plus, the fully protonated version, would have a concentration given by Kb2, where we have hydroxide ion times H2L plus over concentration of HL. That's equal to our 2.13 times 10 to the minus 12. Hydroxide ion and HL concentrations being approximately the same mean that any hydroxide produced from Kb2 reaction, where HL accepts a proton from water, is 7 orders of magnitude smaller than the hydroxide ions produced from the Kb1 reaction. And so we can ignore the contribution from reaction number 2 for all intents and purposes. All right, this is where the fun begins. We're going to calculate the pH of a 0.5 molar solution of leucine, the regular old amino acid. This is a challenging problem because leucine is amphiprotic, meaning it can act like an acid or it can act like a base. When leucine acts like an acid, what we have seen is that it can donate a proton. And this deprotonation event was associated with a value Ka2 that we assigned the numerical quantity 1.8 times 10 to the minus 10 for. As a base, leucine can accept a proton from water. When leucine acts like a base, it reacts with water to form the fully protonated version of leucine and generate hydroxide ions. We described this reaction by Kb2, and it had a numerical value of 2.13 times 10 to the minus 12. Because the Ka2 value and the Kb2 value for leucine acting like an acid or like a base respectively are within 2 orders of magnitude of each other, we can't make the simplifying assumption that leucine acts predominantly like an acid nor predominantly like a base. So the only way for us to approach this problem is to use a systematic treatment of the equilibrium. We need to consider both the charge balance in a solution of leucine and the equilibrium constants that pertain to the solution and anything in it. Our charge balance will tell us that the total number of positive charges is equal to the total number of negative charges in solution. In a solution of leucine, any H plus that's generated plus any fully protonated form of the amino acid must be equal to the total number of negative charges, any leucinate that's generated, plus any hydroxide ion that's produced. Secondly, from our equilibrium constants, we know from our reactions charted out up above that Ka2 is equal to the concentration of H plus times the concentration of L minus over the concentration of HL. I know that eventually I would like to solve for pH. So the first thing that I'm going to do is rearrange this equilibrium constant expression to solve for at least one component of my charge balance equation up above. I'm going to rearrange this to solve for L minus. So take everything else to the opposite side, and we have Ka2 times HL concentration divided by H plus concentration. There's one equation for us to use moving forward. Secondly, our Kb2 expression gives us concentration of OH minus times H2L plus concentration divided by HL concentration. And again, because I want to solve for components of my charge balance equation up above, I'm going to rearrange the Kb2 expression to solve for the fully protonated form of leucine H2L plus. So I'll just bring everything over to the other side, and similarly we get Kb2 times HL divided by hydroxide ion concentration. This is a second equation that I can use and plug into my charge balance expression up above. But it doesn't quite get me to the point where I can solve for a pH yet. Ultimately, what we'll be after is the concentration of hydrogen ions at equilibrium. So there's one more thing that we have to consider in solution, Because these Ka and Kb values are small, we can also consider the effect of water's autoionization. Kw is H plus times OH minus concentration. I'm going to solve this for OH minus, so I can again find one more thing to plug in my charge balance equation up above. The concentration of OH minus, Kw over H plus from autoionization of water. So let's start plugging in these expressions to our charge balance equation. So I want to solve this charge balance equation just for H plus. H plus concentration plus H2L's concentration, which we've already solved for up here, is Kb2 times concentration of HL over concentration of OH minus. That's equal to L minus. We've solved that concentration here in our first step from our equilibrium constants. That's Ka2 times HL concentration divided by H plus concentration plus hydroxide ion, which we've got from our autoionization of water. That's Kw over H plus concentration. The next thing that I'm going to recognize here is that Kb2 we have already seen can be written as Kw over Ka1, or concentration of H plus times concentration of OH minus all over Ka1. If we substitute this entire expression for Kb2 up above, what we end up with is concentration of H plus as our first term still, plus now concentration of H plus times concentration of HL over Ka1 is equal to Ka2 times concentration of HL over concentration of H plus Kw over concentration of H plus. And the next thing that I'd like to do is to be able to solve for H plus. So I'm going to get rid of H plus in all of the denominators on the right-hand side by multiplying every term in this equation through by H plus. When we do that, we get a term of H plus squared plus H plus squared times HL over Ka1 is equal to Ka2 times HL plus Kw. I want to get rid of H plus. I want to get it all on one side. So I'm going to factor out a term of concentration of H plus squared on one side of an equation. We'll be left with 1 plus concentration of HL over Ka1 is equal to Ka2 times HL concentration plus Kw. I'm going to move the entirety of this term in parentheses over to the right-hand side. We'll end up with concentration of H plus squared is equal to Ka2 times concentration of HL plus Kw divided by 1 plus concentration of HL over Ka1. I want to simplify this right-hand side down a little further, and I want to take the square root of both sides of this equation. So what I'll do is multiply every term on the right-hand side of this equation by Ka1. We'll get the concentration of H plus is equal to the square root of Ka1 times Ka2 times concentration of HL plus Ka1 times Kw, all divided by Ka1 plus concentration of HL. And that's all there is to it. This is all we have to worry about in order to solve for the concentration of H plus cations in our leucine solution. Now, that's a whole lot of numbers there. We need to know what the concentration of HL is, but because HL leucine is a weak acid, we expect that the concentration of leucine at equilibrium to be approximately equal to the initial concentration of leucine that we placed in solution. Remember that we call this initial concentration the formal concentration, F. So we can once more rewrite this equation as the concentration of H plus is equal to the square root of Ka1 times Ka2 times the formal concentration plus Ka1 times Kw all over Ka1 plus the formal concentration. This is the explicit equation used to solve for the concentration of H plus in leucine. We can go ahead and do that with our problem that we were given originally. What's the pH of a 0.5 molar leucine solution? We'll end up with the concentration of H plus is equal to the square root of Ka1, that's 4.7 times 10 to the minus 3, times Ka2, that's 1.8 times 10 to the minus 10, times the formal concentration of leucine, 0.5 molar, plus Ka1, again, 4.7 times 10 to the minus 3, times Kw, that's 1 times 10 to the minus 14 at 25 degrees Celsius, all divided by Ka1 plus the formal concentration. Solving all of this, we get the concentration of H plus in this solution is equal to 9.16 times 10 to the minus 7 molar. And therefore, the pH is the negative log of that quantity, 6.04. So that's not too bad, right? We just have to remember a big, long equation that we could derive ourselves from a systematic treatment of equilibrium, taking charge balance and equilibrium constants into account. But even still, there might be a more direct method, a shortcut way, to figure out what the concentration of H plus cations is in solution and make our lives easier when we're dealing with amphiprotic substances. So let's consider again the equation that we just derived. Notice that in the equation that we just derived, Ka1 times Kw is a really, really small quantity. It was significantly less than Ka1 times Ka2 times our formal concentration. That means that Ka1 times Ka2 times our formal concentration plus this whole term is effectively equal to Ka1 times Ka2 times our formal concentration. In other words, we can approximate the concentration of H plus in our leucine solution like this. And in this particular case, and in many other cases as well, the value for Ka1 is going to be significantly less than the formal concentration, so that the denominator of this term can also be simplified. Because Ka1 is often much, much less than the formal concentration of weak acids or amphiprotic materials that we're working with, it's often useful if we approximate this concentration of HF in this way: Ka1 times Ka2 times our formal concentration divided by our formal concentration. In this result, formal concentration isn't necessary. So let's manipulate the result of this equation. Let's square both sides again, and we'll get concentration of H plus squared is equal to Ka1 times Ka2. All right, well, just for the heck of it, let's also take the negative log base 10 of both sides, just because that's what you do when you're doing math. Remember, the rules of logarithms say that the log of a quantity raised to an exponent is the same as that exponent multiplied by the log of a quantity. So on the left-hand side of this equation, we can use 2 times the negative log base 10 of the concentration of H plus cations. On the right-hand side, remember that another rule of logarithms tells us that the log of a product is the same as the sum of logs. So we can apply that rule here. The log of Ka1 times Ka2 is the same as the log of Ka1 plus the log of Ka2. Now, recognize that the term negative log of H plus concentration is pH. Negative log of Ka1 is pKa1. Negative log of Ka2 is pKa2. And we've got this pesky little 2 over here to divide everything through. A useful approximation for amphiprotic substances is that the pH of a solution prepared from an amphiprotic substance of substantial concentration, where the concentration, the formal concentration of our substance, is significantly larger than the Ka value for the first deprotonation event for that substance, is this equation. The pH of our amphiprotic solution is pKa1 plus pKa2 divided by 2. Let's apply this equation as a good first approximation to our pH of our leucine solution. pKa1 for leucine is the negative log base 10 of 4.7 times 10 to the minus 3. Here that's equal to 2.33. Similarly, we can calculate the pKa2 of leucine, and that ends up being 9.74. Together then, our pH of our 0.5 molar solution of leucine should be approximated as 2.33 plus 9.74 divided by 2. This results in a pH of approximately 6.04, which matches the pH that we calculated earlier with a lot less work. So, to a good approximation, we get effectively the same pH from this shortcut method as we do from the full systematic treatment of equilibrium.